Okay, now we're looking at our last section, Hess's law, Mr. Hess. In going from a particular set of reactants to a particular set of products, meaning reactants to products, the change in enthalpy is the same whether the reaction goes in one step or a series of steps. So the idea is, again, all the steps, as long as they're all additive together, are going to provide us the same amount of energy. Whether it's me in part A, reactants to products, straight path, like unloading the dishwasher, or Mrs. Arcani loading the dishwasher a couple times throughout the day. Regardless of the path taken, you still get to the same place, although path B drives me bonkers. But enough being said is that multiple paths can still get us to the same amount of energy. So there's some relationships that multiplying a reaction to change the number of coefficients will multiply it by that factor. Since enthalpy is extensive, means it depends on how much there is. If you doubled the amount, you double the amount of heat for the reaction. Reversing a reaction to flip changes the products and reactants, also changes the sign. So if we are going from carbon-oxygen to carbon dioxide, it releases energy. To go from the compound to its constituent elements will be an addition of energy, which makes sense. Breaking bonds to form elements, energy in. Elements making bonds, you're going to release energy. So we utilize these two ideas in order to determine enthalpy of reactions from many of our different reactions that we have occur. Now there's this idea of what's called standard conditions. This is what we'll often deal with, and then on a few occasions we'll deal with non-standard conditions, usually in later sections. So the state of the material needs to be if it's a pure gas at 1 atmosphere, pure solid or liquid in its most stable form at 1 atmosphere pressure, temperature of interest usually 25 degrees Celsius, and substances in a solution with a concentration of 1 molar. So these are our standard conditions. You see a whole bunch of ones. Obviously we don't have 1 degree Celsius, but usually 25 degrees Celsius. So this is our standard state, because then from here, other things can be different based off different pressures, temperatures, and concentrations. So standard enthalpy change, you see what that's a little symbol, looks like, I guess, the degree symbol, is when enthalpy change when all reactants are in their standard states. Again, going back, this would be the fact that if it was a gas, 1 atmosphere, solid or liquid, 1 atmosphere, temperature 25 degrees Celsius, and if it was an aqueous solution, 1 molar concentration. These would be different if those were not standard state. So that's what this means. You can have delta H values that are not standard conditions, but we would not write that in. Again, that comes about later in the year. So this is where we've had the enthalpy of formation at standard state, 1 mole. Remember, elements need to be in their standard states. Heat of formation of pure element is, again, 0. Includes all the diatomic gases. So when we think about it, something like O2 is 0. O, just monatomic, 1 atom of oxygen in a mole, is actually not 0. But again, you would have to find a enthalpy of formation value in order to do any calculations with it. So keep that in mind. You're not likely to see that. So let's take an example. Combustion of methane. We've already done this, right? But we used enthalpies of formation. Here we have individual reactions. These are enthalpies of formation that we had, right? All these being formed. These values may look kind of familiar to you. But what we're doing here is we're trying to determine from reaction states. So we have our first reaction because we need to have CH4 appear on the reactant side. So we can see that reaction is over here. We need to flip it in order to get a positive value and get methane, CH4, on that side. Next, we need to have oxygen on the left side. We see that we have 2 possibilities here. We're going to choose the CO2 because we need CO2 on the right side as well. So I'll take it as is. 1 more additional because we need to have water on the other side. And I see I need 2 waters, so I need to multiply that times 2. Add it all up, we get the same values we got from the last one. I'll just double check my values here. Yep, because that was in a liquid state. It's in a liquid state. That doesn't seem to be mentioned here, but that's the way it was. So we can see things that are on the right and left, just like in math, we can cancel them out, leaving us with our CH4, 2O2, CO2, and 2H2O. Another example, we've got this chemical equation we're trying to get to, and we have our two possibilities. So first need to see that we have NaCl on the left side, and I need two of them. So I need to reverse it and multiply it times 2. Again, everything in the equation times 2. Next, I see I need nitrogen and oxygen on the right side, so I need to flip that other one and times it by 2. Then add them up. Careful to watch your negatives in order to get your correct answer. Another example. Again, given these three different types, what do we want to go through here? Well, I first need iron 2 oxide on the right side. I see this is the only one that has that. That's always the place I try to start, where you only have one place for each of those. And I see I need only one of those. So take it, flip it, times it by 1/3, and that goes with everything involved. The next one, I see I need CO on the left side, and I have CO2 on the other side. So I can see I've got a couple conditions that both have CO and iron 2,3 and 3,4. So I need to be careful with what I already have given. I have 2,4 being present. And I see my subscript is incorrect. This should be Fe3O4. So I have my FeO in the right space. Next, I want to work at eliminating what's not in the equation. And I'm going to choose Fe2O4 because those are only unique in each of these, while my CO2s and COs are kind of all over the place. So I'm going to take my Fe2O4 or Fe3O4, and I see it's 1/3. So I need to take equation 1, flip it, and multiply it times 1/6. So Fe3O4 will be canceled out. I'm going to stick with that idea that now my 1/2 Fe2O3 is on my product side. I need it gone. So I need 1/2 Fe2O3 on the reactant side. And so I'm going to use reaction 2 and multiply it times 1/2. So I've eliminated my Fe3O4. I've eliminated my Fe2O3. Now I need to clean up my carbon monoxides and carbon dioxides. So on the left-hand side, I see I have 1/3 and 1/6 CO2. That actually is half CO2. I see I have 3/2 CO2. So get rid of the half. From the 3/2, that gives me 1 CO2. Over here I have 1/3 and 1/6 carbon monoxide. I have 3/2 carbon monoxide. A half over here minus a half gives me 1 carbon monoxide, and I have 1 iron available. So overall, adding it all up, I get negative 11 kilojoules. And you're only going to use one reaction at a time. Now, you might think, does it make a difference on which order I go? Technically, no, it doesn't. However, sometimes if you start with, let's say, this one in the middle, where everything is eliminated, it can make it hard to think of what's my next step. So it's really just a puzzle. Sometimes it can be really hard, but it's just a puzzle. Just like if when you make a simple puzzle piece working from the outside in, or you start from the inside out, one can make it more challenging than another. There's no real tricks. You just need to get some practice, figure out which is which. And again, if you go in a different order, it can take a longer time because it's harder to see where the next puzzle piece goes. So again, my recommendation is go for the things that are unique on either side. Start with one place where you're trying to find one of your reactants. And then once you've produced that in the product side, try to eliminate that on the next one, and maybe even on the next one. You see iron just kind of fell into place. Come in with any kind of questions, and this, I think, concludes Unit 6. Take care.